NEC Section 250.118 specifies the requirements for the installation of grounding electrode conductors, often referred to as GEC. It stipulates that grounding electrode conductors must be installed in raceways or other forms of protective enclosures if they are situated in concealed locations. To dissect this regulation effectively, we must clarify several essential aspects. Firstly, we need to define what constitutes a grounding electrode conductor. Secondly, we must understand what the code means by a concealed location. Thirdly, we should explore the types of raceways that are suitable for GEC installation. Fourthly, we need to examine the rationale behind the requirement for raceway protection. And finally, we need to consider instances where the rules might permit exceptions. A grounding electrode conductor is a crucial component of an electrical grounding system. Its primary purpose is to connect the electrical system's grounded conductor, which is typically the neutral conductor, or the equipment grounding conductors, to a grounding electrode. A grounding electrode is a conducting object that establishes a direct electrical connection to the earth. Common examples of grounding electrodes include metal underground water pipes, metal frames of buildings when effectively grounded, concrete encased electrodes, and ground rods. The grounding electrode conductor's role is to provide a low impedance path for fault current to return to the source, which facilitates the rapid operation of overcurrent protective devices such as circuit breakers and fuses. This, in turn, minimizes the risk of electrical shock and equipment damage. The National Electrical Code defines a concealed location as a location that renders the wire inaccessible without removing parts of the building structure or finish. Examples of concealed locations include inside walls, above ceilings, and under floors. If a grounding electrode conductor runs through any of these areas, it is deemed to be in a concealed location. The code necessitates that GEC in concealed locations must be protected within raceways or enclosures. This protection is not just about physical damage, but also about minimizing the risk of corrosion and accidental contact. The NEC provides a variety of options when it comes to selecting suitable raceways for grounding electrode conductors. Some of the most commonly used types include rigid metal conduit, also known as RMC, intermediate metal conduit, known as IMC, electrical metallic tubing, referred to as EMT, rigid polyvinyl chloride conduit called rigid PVC, and electrical non-metallic tubing, known as ENT. Each of these raceway types offers different levels of physical protection and resistance to environmental factors. For example, RMC and IMC are typically used in locations where there is a high risk of physical damage, while EMT and rigid PVC are often used in less demanding environments. The choice of raceway should be based on a careful assessment of the specific conditions at the installation site, taking into account factors such as the likelihood of impact, exposure to corrosive substances, and temperature variations. The rationale behind requiring raceway protection for grounding electrode conductors in concealed locations is rooted in safety and reliability. Firstly, raceways provide physical protection to the conductor, shielding it from damage that could result from nails, screws, or other objects that might penetrate a wall or ceiling. Secondly, raceways protect the conductor from corrosion, which can degrade its conductivity and increase the impedance of the grounding path. Thirdly, raceways prevent accidental contact with the conductor, which could pose a shock hazard to individuals working on or near the electrical system. Fourthly, raceways help to maintain the integrity of the grounding system over time, ensuring that it continues to function effectively in the event of a fault. While the NEC generally requires raceway protection for grounding electrode conductors in concealed locations, there are some exceptions to this rule. One common exception applies to short runs of GEC that are securely fastened to the surface and are not subject to physical damage. For instance, a short length of GEC that connects a grounding electrode to a service panel might be permitted to run without a raceway, provided that it is adequately supported and protected from impact. Another exception may apply in situations where the GEC is installed in a dedicated electrical room or closet, where access is restricted to qualified personnel. In these cases, the authority having jurisdiction, also known as the AHJ, may waive the raceway requirement, provided that the conductor is adequately protected from physical damage and accidental contact. In summary, NEC Section 250.118 mandates that grounding electrode conductors in concealed locations must be installed in raceways or enclosures. This requirement is intended to protect the conductor from physical damage, corrosion, and accidental contact, and to ensure the long-term reliability of the grounding system. While there are some exceptions to this rule, they are typically limited to situations where the conductor is adequately protected by other means. When installing grounding electrode conductors, it is essential to carefully review the applicable code requirements and to consult with a qualified electrical inspector or engineer to ensure that the installation complies with all relevant safety standards. Consider a scenario where a new commercial building is under construction. The electrical design calls for a dedicated grounding electrode system that consists of multiple ground rods driven into the earth. The grounding electrode conductors that connect these ground rods to the main service panel must be routed through the interior walls of the building. Because these conductors are located in concealed locations, they must be installed in raceways in accordance with NEC Section 250.118. The electrical contractor decides to use rigid metal conduit, RMC, for this purpose. RMC is chosen because it provides excellent physical protection and is resistant to corrosion. The RMC is installed before the walls are closed up and the grounding electrode conductors are carefully pulled through the conduit. The conduit is securely fastened to the building structure and all connections are made in accordance with the manufacturer's instructions. Once the walls are closed up, the grounding electrode conductors are fully protected from damage and corrosion. This ensures that the grounding system will function reliably for the life of the building. Another scenario involves a telecommunications closet located within an office building. The telecommunications equipment in this closet requires a dedicated grounding system to protect it from electrical surges and noise. A grounding electrode conductor is installed to connect the equipment grounding busbar in the closet to the building's main grounding electrode system. This grounding electrode conductor is routed through the ceiling space above the closet. Because the ceiling space is considered a concealed location, the grounding electrode conductor must be installed in a raceway. In this case, the electrical contractor opts to use electrical metallic tubing or EMT. EMT is a lightweight and cost-effective raceway solution that provides adequate protection for the conductor in this environment. The EMT is installed before the ceiling tiles are installed, and the grounding electrode conductor is carefully pulled through the tubing. The tubing is securely fastened to the ceiling structure, and all connections are made in accordance with the manufacturer's instructions. Once the ceiling tiles are installed, the grounding electrode conductor is protected from damage and accidental contact. This ensures that the telecommunications equipment is properly grounded and protected from electrical disturbances. Let's also consider a residential application. A homeowner decides to install a backup generator to provide power during outages. The generator requires a grounding electrode system that is separate from the home's main grounding system. A ground rod is driven into the earth near the generator, and a grounding electrode conductor is installed to connect the generator's grounding terminal to the ground rod. The grounding electrode conductor is routed along the exterior wall of the house. In this case, the homeowner may be tempted to run the grounding electrode conductor without a raceway since it is not located in a concealed location. However, even though the conductor is exposed, it is still subject to physical damage and corrosion. Therefore, it is recommended that the grounding electrode conductor be installed in a raceway, such as rigid PVC conduit, to provide adequate protection. The PVC conduit is securely fastened to the exterior wall, and the grounding electrode conductor is carefully pulled through the conduit. The conduit protects the conductor from weather impact and accidental contact. This ensures that the generator's grounding system will function reliably in all conditions. It is important to note that the specific requirements for grounding electrode conductor installations may vary depending on local codes and regulations. Therefore, it is always advisable to consult with a qualified electrical inspector or engineer to ensure that the installation complies with all applicable standards. They can provide guidance on the selection of appropriate raceway types, the proper methods for installing raceways, and any other specific requirements that may apply in your area. Proper grounding is essential for electrical safety and equipment protection. By following the requirements of the NEC and consulting with qualified professionals, you can ensure that your grounding system is installed correctly and will provide reliable performance for years to come. Furthermore, consider the importance of proper bonding within the raceway system itself. When metallic raceways such as RMC, IMC, or ENT are used to enclose grounding electrode conductors, it is crucial to ensure that the raceway sections are properly bonded together. This bonding creates a continuous electrical path that is capable of carrying fault current. Without proper bonding, the raceway itself could become energized in the event of a fault, posing a shock hazard. Bonding is typically accomplished by using threaded couplings, bonding bushings, and bonding jumpers. Threaded couplings provide a secure mechanical and electrical connection between sections of raceway. Bonding bushings are installed on the ends of raceways where they enter enclosures or panels. These bushings have a sharp edge that bites into the metal of the enclosure, creating a low impedance connection. Bonding jumpers are short lengths of wire that are used to connect sections of raceway that are not directly connected to each other. For example, a bonding jumper might be used to connect a section of raceway that is interrupted by a non-metallic fitting. Another important consideration is the size of the grounding electrode conductor. The NEC specifies the minimum size of the grounding electrode conductor based on the size of the service entrance conductors. The larger the service entrance conductors, the larger the grounding electrode conductor must be. This is because the grounding electrode conductor must be capable of carrying the maximum fault current that the system is likely to experience. Using a grounding electrode conductor that is too small can result in inadequate grounding and increased risk of electrical shock. The NEC provides tables that specify the minimum size of the grounding electrode conductor for various service entrance conductor sizes. These tables should be consulted to ensure that the grounding electrode conductor is properly sized. The material of the grounding electrode conductor is also a factor to consider. Copper is the most common material used for grounding electrode conductors because it has excellent conductivity and corrosion resistance. However, aluminum is also permitted in some cases. When aluminum grounding electrode conductors are used, they must be properly sized and protected from corrosion. Aluminum conductors are more susceptible to corrosion than copper conductors, so it is important to use appropriate connectors and coatings to prevent corrosion. Additionally, aluminum grounding electrode conductors must be installed in a way that prevents them from coming into contact with dissimilar metals, which can also lead to corrosion. Let's delve into the specifics of NEC section 250.118, which lists the acceptable types of grounding electrode conductors. This section is crucial for ensuring that the chosen conductor is suitable for its intended purpose and meets the safety requirements of the electrical code. The NEC recognizes several types of conductors for use as grounding electrode conductors, each with its own characteristics and applications. These include copper, aluminum, and copper-clad aluminum. Copper conductors are the most widely used due to their excellent conductivity and resistance to corrosion. They are suitable for both indoor and outdoor applications and can be used in direct burial situations. Aluminum conductors are lighter and less expensive than copper conductors, but they have lower conductivity and are more susceptible to corrosion. When used as grounding electrode conductors, aluminum conductors must be properly sized and protected from corrosion. Copper-clad aluminum conductors combine the advantages of both copper and aluminum. They consist of an aluminum core with a copper cladding, providing good conductivity and corrosion resistance at a lower cost than solid copper conductors. In addition to the conductor material, NEC section 250.118 also specifies the acceptable forms of grounding electrode conductors. These include solid conductors, stranded conductors, and busbars. Solid conductors are single, unbroken wires that are typically used for smaller grounding electrode conductors. Stranded conductors consist of multiple smaller wires twisted together, providing greater flexibility and ease of installation. Busbars are rigid metal bars that are used for larger grounding electrode conductors, providing a low impedance path for fault current. The choice of conductor form depends on the size of the grounding electrode conductor, the application, and the installation requirements. Another important aspect of grounding electrode conductor installation is the method of connection to the grounding electrode. The NEC specifies that grounding electrode conductors must be connected to grounding electrodes using approved methods such as exothermic welding, listed connectors, or bolted connections. Exothermic welding involves using a chemical reaction to create a permanent molecular bond between the conductor and the electrode. This method provides a very low impedance connection that is highly resistant to corrosion. Listed connectors are connectors that have been tested and certified by a recognized testing laboratory, such as Underwriters Laboratories, known as UL. These connectors are designed to provide a reliable and safe connection between the conductor and the electrode. Bolted connections involve using bolts, nuts, and washers to mechanically and electrically connect the conductor to the electrode. These connections must be properly torqued and protected from corrosion. The choice of connection method depends on the type of grounding electrode, the conductor material, and the installation conditions. Let's also discuss the importance of protecting grounding electrode conductors from physical damage. While NEC Section 250.118 requires raceways for concealed locations, it is also important to protect grounding electrode conductors in exposed locations from physical damage. This can be accomplished by using raceways, enclosures, or other protective measures. In areas where the grounding electrode conductor is subject to impact or abrasion, it should be protected by a rigid raceway, such as RNC or IMC. In areas where the grounding electrode conductor is subject to corrosion, it should be protected by corrosion-resistant raceway, such as rigid PVC or stainless steel. In areas where the grounding electrode conductor is subject to vandalism or theft, it should be protected by a locked enclosure or other security measures. The specific protection measures will depend on the environment and the potential risks. Furthermore, it is essential to maintain the accessibility of grounding electrode conductors for inspection and maintenance. The NEC requires that grounding electrode conductors be accessible for inspection and testing. This means that the conductors should not be buried or concealed in a way that prevents them from being visually inspected and tested. Access can be provided by using removable covers, access panels, or other means. Regular inspection and testing of grounding electrode conductors can help to identify potential problems such as corrosion, loose connections, or physical damage. These problems can then be corrected before they lead to a more serious electrical hazard. Consider the case of a large data center with sensitive electronic equipment. The data center relies on a robust grounding system to protect its equipment from electrical surges and noise. The grounding electrode conductors in the data center are routed through a network of cable trays and conduits. To ensure the integrity of the grounding system, the data center operators implement a regular inspection and maintenance program. This program includes visual inspections of the grounding electrode conductors, testing of the grounding connections, and cleaning of the grounding electrodes. During one inspection, a technician discovers that a grounding electrode conductor has been damaged by a forklift. The technician immediately repairs the damaged conductor and reinforces the protection around it. This prevents a potential grounding failure that could have damaged the data center's equipment. Another example is a hospital with critical life support systems. A hospital's electrical system must be highly reliable and safe. The grounding electrode conductors in the hospital are routed through a dedicated grounding network that is separate from the normal power distribution system. To ensure the reliability of the grounding system, the hospital implements a comprehensive testing and maintenance program. This program includes regular testing of the grounding impedance, inspection of the grounding connections, and monitoring of the grounding voltage. During one test, an engineer discovers that the grounding impedance is higher than expected. The engineer investigates the cause of the high impedance and discovers that a grounding electrode has corroded. The engineer replaces the corroded electrode and restores the grounding system to its proper operating condition. This prevents a potential grounding fault that could have jeopardized the operation of the hospital's life support systems. Finally, let's discuss the importance of documenting grounding electrode conductor installations. The NEC requires that grounding electrode conductor installations be documented in the electrical system drawings and specifications. This documentation should include the size, material, and location of the grounding electrode conductors, as well as the methods of connection to the grounding electrodes. Proper documentation is essential for future maintenance, repairs, and upgrades to the electrical system. It also helps to ensure that the grounding system is properly installed and maintained over time. In summary, grounding electrode conductors are a critical component of electrical safety. By following the requirements of the NEC, protecting conductors from damage, maintaining accessibility, and documenting installations, you can ensure that your grounding system is safe, reliable, and effective. Remember to consult with qualified electrical professionals and local authorities to ensure compliance with all applicable codes and regulations. This will protect people and equipment from electrical hazards and ensure the long-term performance of your electrical system. This includes everything from residential to commercial installations, where grounding is a key element in the design and ongoing electrical safety requirements.